All right, so we're already familiar with square roots a little bit, at least, probably. So we'll just remember, we define the square root of a number to be the number which, when we multiply it by itself, gives us that number in the radical. Like the square root of 9 is 3, but that definition doesn't quite suffice because there are two numbers we can square to get 9, right? If I square 3, I get 9. If I square -3, I get 9. Right, so that begs the question, is the square root of 9 equal to 3, or is it equal to -3? So 9 does have two square roots, but we want to be particular about what we are referring to when we talk about the square root of 9. So if we see a radical sign, right, like square root of a, that always means the positive root or the principal root of the number. So this guy right here, that's called the radical sign. So in fact, now we have an answer. The square root of 9 is equal to 3, not -3. But if I want to refer to the negative square root of 9, I simply just put a negative out in front of it. We define other roots analogously. The cube root of a number a is written using the same kind of notation, only we put this little number 3 in the crook of that radical sign. So that means it's the cube root. And in general, the principal nth root of a number is the number which, when raised to the nth power, yields a. So the nth root, the principal nth root, we denote that way. So again, we just put that little number n kind of in the crook of the radical. And it's defined to be the number which, when we raise it to the nth power, gives us a. The square root is the only one where we don't write the little number in the crook. Technically, if I wanted to put the 2 in there, I could, and that would still mean the square root. But if we see it without any number in there, it means the square root. So we're going to evaluate some roots. These are convenient numbers. We can evaluate all of these really without a calculator. The cube root of 27 is equal to 3, and that's because 3 times 3 times 3 is equal to 27, right? 3 cubed is equal to 27. The square root of 0.04 is equal to, now this one might be a little harder to do in our heads. We're going to talk about some properties of radicals that'll make it a little bit easier, but for now I'm just going to observe that the square root of 0.04 is equal to 0.2, and that is because 0.2 squared, which is 0.2 times 0.2, is equal to 0.04. The cube root of -8 is equal to -2, and that's because -2 cubed, which is -2 times -2 times -2, is equal to -8. So a lot of what we do in this section is gonna be simplifying radicals, trying to write an expression that involves a radical in its simplest form. So a radical expression is simplified if all nth powers have been removed, so there's no square factors in a square root, there's no cube factors in a cube root, and so on. We don't want any radicals in the denominator of a fraction, and we don't want fractions inside the radical. So we really want to be able to express it as just some number times a simple radical with no perfect nth powers. There's a couple of properties that will be particularly useful, and these really stem directly from the fact that we can distribute, you might recall, we can distribute an exponent over a product, over multiplication, and over division. This is an extension of that property that says we can split up a radical over multiplication, and we can also split up a radical over division. We should be really careful and note that we cannot split up a radical under addition or subtraction. And that's for the same reason that we can't distribute an exponent over addition or subtraction. So we're going to simplify some radicals here. Now, there's probably a couple different ways we can think about it. And the easiest way that I know to think about simplifying a radical is by factoring. So I'm going to factor 40. I'm going to make a little factor tree here. So 48 is 12 times 4, and 12 is 2 times 6, and 6 is 2 times 3, and 4 is 2 times 2. I've factored it all the way down to primes. If you go all the way down to primes, you'll always be able to kind of finish this process. Sometimes if you notice the same factor showing up, you don't have to go all the way down to primes. I factored this all the way down to primes, so now I'm just going to write it out. I've got 1, 2, 3, 4 factors of 2 and a factor of 3. This is a square root, and with a square root, what I'm looking for is 2 of the same factor. And if I have 2 of the same factor, I could take that pair and bring out a single factor. So I've got a 2 here, I've got another 2 here. And so when I bring those out, there's my first pair of 2's, comes out as a single 2. My second pair of 2's comes out as a single 2. If you're bringing out more than one factor, you multiply them together outside. And then I've got a 3 left over. So this is 4 times the square root of 3. And there's a simplified form. Now I mentioned before, like if you happen to notice, a pair of factors in a square root, you don't always have to go all the way down to primes. And I'll just point out that 48 is, let's see, we had 12 times 4, and 12 is 4 times 3. So if I didn't want to go all the way down to primes, I could have noticed, oh, I've got a 4 here, so that the square root of 48 is the square root of 4 times 3. Here's a pair of 4's. We can bring out a single 4, and then we're left with a 3 inside. Right, exactly the same as what we already got. If you're unsure if you've done this correctly, at least on a numerical example, right, this is just constants, numbers inside the radical, you can check. And I could check to see if I've simplified correctly by doing 2 things on the calculator. First I'll do square root 48. And it'll give me this decimal approximation. Next I'll put in what I got when I simplified it, which was 4 times the square root of 3. And you'll notice I get exactly the same approximation, so I know that I've simplified correctly. Okay, next we've got the cube root of 40. This is a cube root, so I'm going to be looking for a group of 3 of the same factor in order to bring one of them outside. So 40, let's make a factor tree. 40 is 8 times 5, and 8 is 2 times 4, and 4 is 2 times 2. So this is the cube root of 2 times 2 times 2 times 5. And there we've got a group of 3 factors of 2. That means I've got 1 factor of 2 I can bring out. 2 times the cube root of 5. And again, I can check, because it's a numerical example, I can check the cube root of 40. Now in the calculator, it's got the square root built right in. To access the cube root, you got to hit the math key. Option 4 here is the cube root of 40. And then we simplified to 2 times the cube root of 5. So 2 times the cube root of 5. And you'll see I got exactly the same approximation. So these are equal. All right, next we have 1 over the cube root, 1 over the square root of 3. We want to simplify this, and 3 is prime, so clearly there's no square factors we're going to bring out. But you'll notice we have a radical in the denominator. We like to avoid that when we're simplifying radicals. So we want to get rid of that radical in the bottom, and we have a pretty simple technique to do it. So the issue here is that I've got the square root of 3 in the bottom, and I'm going to fix it by multiplying the top and the bottom by the same thing, which I know I'm allowed to do. And here I'm going to pick the square root of 3. Up top, 1 times the square root of 3 is the square root of 3. On the bottom, the square root of 3 times the square root of 3 is 3. I mean, by definition, right? The square root is that thing which, when multiplied by itself, gives you the number inside. So this is the square root of 3 times the square root of 3. The square root of 3 divided by 3 is how this simplifies. I'm going to do an extra example here. Depending on what you're looking at, what you're starting with, will depend on what factors you need to add in. So here, when it's a square root that's in the bottom, it suffices just to multiply it by that square root on the top and the bottom. However, suppose I had 1 over the cube root of 3. So now I need 3 factors of the cube root of 3, right, in order to get rid of the radical. So what I need to do is multiply by not just the cube root of 3, but the cube root of 3 squared, right? I need 2 factors of the cube root of 3. So if I have 3 factors of the cube root of 3, then I can get rid of the radical and I just get 3, and that's what we've got in the bottom. So in the bottom I have 3. Up top I have the cube root of 3 times the cube root of 3, or the cube root of 3 squared, and that is the cube root of 9 over 3. So there's a little extra example here. This, what we call the index of the radical, or the order of the radical, this number, like in the crook of the radical sign, tells you how many factors of that radical you need in order to be able to get rid of the radical sign. Also important to note here is that the 3 and the 9, we can't cancel. Just like we can't cancel the 3 and the 3. And that's because one number's in the radical and one number's outside the radical, so they're off limits for canceling. Alright, let's do another one here. We have the square root of 3 over 75. Now, I could split up the radical first and then simplify, but one thing I'm noticing here is that 3 actually goes into 75. So I could reduce the fraction first. 3 goes into 75 25 times. And now it'll be easier. Now when I split up the radical, I've got the square root of 1 over the square root of 25. And this is 1 over 5. Those are both perfect squares, so it's fairly simple to split up, to simplify. Now, I'm going to do a little extra work here, a little bonus work on this. Let's say you didn't think about reducing the fraction first. Let's say you looked at this and your first instinct was, well, I'm going to split up the radical over division. That's okay. It'll be a little bit more work to finish it, but it's still okay to do. So when we split up this radical, the square root of 3 on top, that's already simplified. So first I'm going to just work on simplifying the square root of 75. So that's 25 times 3, and 25 is 5 times 5. So we have now the square root of 5 times 5 times 3. We have a pair of 5s in here we can take out, a single 5. And now I've got the square root of 3 and the square root of 3, common factor on the top and the bottom, so we can cancel those and we get 1 over 5, just like we got. So if you didn't notice initially that you could reduce the fraction, you could still get to the right answer. It might just take you a couple more steps. Next example, we have the square root of 6 squared plus 18. So right off the bat, I just hope that when we see this, we're making ourselves slow down. We got addition happening in there, and a lot of properties that work out nicely when we're multiplying and dividing don't hold when we are adding or subtracting. We cannot split up a radical over addition. So what I'm going to do is just follow the order of operations. I'm going to evaluate what's inside that radical. 6 squared is 36. 36 plus 18 is 54. So now what I want to do is simplify this radical. Let's make a little factor tree. So this is 2 and 27. 27 is 9 times 3, and 9 is 3 times 3. So this is the square root of 2 times 3 times 3 times 3. We can take out a pair of 3's. Right, there's a pair of 3's. That'll come out as a single factor of 3 outside the radical. And then inside I'm left with 2 times 3, or 6. Alright, one more example to go. This one's got variables in it. That's okay. The same principle applies. This is a cube root, and that means I'm looking for groups of like 3 of the same factor, or perfect cubes inside, to take out a single factor from the radical. So 24 is 3 times 8. 8 is 4 times 2, and 4 is 2 times 2. So we have 2 cubed times 3. And then x to the 4th. Look, I'm going to write that. I could write x times x times x times x. But since I know I'm looking for perfect cubes, I'm going to take advantage and write a little bit simpler in an exponential form. I'm going to write this as x cubed times x. And then I've got y cubed. Now x to the 4th I could also write as x squared times x squared, or x times x times x times x. But when I write it this way, I chose to write it this way because I know I'm looking for perfect cubes. So I can take out a single factor of 2, a single factor of x, a single factor of y. 2xy, and what's left inside is a factor of 3 and a factor of x. So cube root of 3x. And that is the simplest, simplified form for this radical.